So one of the things I like about the conferences is the traveling part and going to sort of different places. But obviously that's a bit tricky at the moment. But the good thing about Zoom is you can do this at home. But also the good thing about Zoom is that you can do it anywhere. So I decided to keep the traveling part, and I've come here to Gibraltar. So that's where I am at the moment. So forthwith, this conference shall be known as the Gibraltar Conference. And that by me, maybe not anyone else, but anyway. Okay, so the last few months, I've been working on building a Python library, and Python's a programming language, building this library to model PCT systems. And there are some programming bits to this talk, but don't worry about it if you're not a programmer. I think you'll get an idea of what the potential is. So I'm going to mention some Python libraries which are quite useful and very commonly used. I'm going to talk about the Jupyter Notebooks environment, which is a very flexible way for developing programs without having to write whole programs. You do them in small chunks and see the results of what you're doing immediately. Then I'm going to talk about the PCT library, which I've built, and give some examples of that. Okay, so the sort of Python libraries, I mean, Python it's a very common language these days. It's widely used, and it's got hundreds of different packages which you can just import into your environment and use them. And a very common one is NumPy, which stands for sort of numerical Python. And it's sort of a highly efficient numerical computations. It allows mathematical functions, signs, clauses, etc. It allows you to use multi-dimensional arrays, do matrix multiplication, fast Fourier transforms, sets, polynomials, things like that. So it's a very common and powerful library that is used. Another one is OpenAI Gym, and OpenAI is an organization which was founded by Elon Musk, and there's the Gym library which provides you with lots of simulated environments. And the idea behind these was to be able to develop reinforcement learning algorithms, but they can be used for PCT as well, because they provide you with sets of observations or perceptions about the state of the system, and allows you to apply an action to the environment to change those observations. So there's a number of different types of environments that provides. So these ones here are showing some of the classical control ones, like the inverted pendulum and mountain car problem, things like that. There is what is called the MuJoCo environments, which stands for multi-jointed constraints, I think. And there's also some robotics environments, which might be quite useful as well, though I haven't used those yet. Another very good library is called Plotly, and this is an environment for, or a library for visualizing the data or plotting the data. So it provides lots of graphs, plots, charts, etc., all catered to sort of different industries or different disciplines, different areas of study. So machine learning, statistics, scientific charts, financial charts, maps, three-dimensional charts, lots of very useful things which are good for using with PCT as well to visualize the data. Okay, so the Jupyter environment is a way of developing programs with allowing you to see the results of your work immediately. So it's organized within cells rather than in a complete file. So you can run each cell at a time. So here, for example, I'm just doing a print print of hello world, and you can run that cell and you can see the results of what you're doing. You can assign variables, print the variable. You can import a library. So this is importing the NumPy library, giving it an alias of NP, and calling assign on the value which we had up there, and then you can print the result of that. You can do calculations, then print out as you go. And this is quite useful if you have a program which might have one particular part of it which is takes quite a long time. So it's sort of loading in some data or something. You only have to run it once. Then you can add more cells after it and do different types of computations on it. You can write functions and then call functions there and see what the output of them are. With the NumPy, you can create these arrays. So here creates one. It's a two-dimensional array. In this case, it's just of random numbers. But you can create arrays of any number of dimensions. So this next one here is doing 4 dimensions of 2 by 3 by 4 by 2. And we can plot that out and see all of that. Using the Plotly environment or Plotly library, we can import that, create a figure, and then here I'm just going to loop through some random data, and that will print it or plot it on the plot. So it will be done sort of dynamically, and you can see the results in real time. So it's a sort of very easy, this Jupyter notebook is very easy and way of developing programs and getting the results of them quite quickly. Now this I'm running within a environment which I've installed on my machine, a Python environment. But these notebooks, you can also do them completely online, so you don't need to install anything or import anything, or don't need to install anything. And there's what is called the Google Collaboratory environment, which is an online environment of these notebooks, and you can import libraries such as the PCT library into that and run the data on that. Okay, so on to the PCT library. I'll get that out of the way. So here it is. This is where it's stored on or released on the Python website, and there's some brief description of it there. But there's also links to some more detailed explanation of what has been provided or what has been built within this library, and it provides some examples as well. And I'll just run through some examples here on this in this notebook. So the PCT library is made up of functions, nodes, which are individual control units, and hierarchies. So the functions are things that we're familiar with, the integration function, proportional function, things like that. So here I'm just going to import these functions into this notebook environment. So here I'm then going to create 2 functions. One is just a constant function, and one is an integration, a leaky integration function. I provide the parameters to it of the gain and the slow factors. And then I'm going to link those 2 functions together so that the integrator function takes the constant value as its input. And to run the function, you can just call the variable name with the brackets after it. And if I print that out, then it shows the result of integrating one time. For these functions, you can also run them a number of times as well. So this next one is going to run it 10 times, and it will print the output each time. So it's continued the integration of that input variable, which is the constant value of 2. So within Python and within this PCT library, rather than just having inputs as a single value, you can have the input being an array of values as well. So here I create an array of 3 by 3 array with the value of 2 inside it. So I can create a constant function which has that array as the input, and then another integrator function which links to that array. I can run the integrator function, and that will integrate all the values within the array. So you don't have to have single values, you can have them within arrays as well. Here's an example of a weighted sum function, and that is doing the weighted sum of 3 input values. Within this library, you can actually view what it is that you've created. So this gives you a summary of what the weighted sum function is. It shows the weights of it and the links to the other functions. So it will help you to check that you've sort of configured it correctly. You can also print out the configuration of it within this sort of format, which you might know is the JSON format, and this is useful for saving to files. You can also look at what it is you created graphically as well. So this shows the weighted sum with the 3 inputs to it. Generally, you do this in the context of the hierarchy of the system rather than the individual functions, but you can look at them this way as well. So a node, what I've called a node, is a single control unit. And I just create a node here, and we can look at what it is. And that's a single control unit, so that has a reference function, perceptual function, comparator function, and output function. And if we print that out, so we can view it graphically. So that's what it looks like. That's a single control unit with the perception and the reference here with the comparator, and then an output function there. Obviously, when you create it from scratch like this, it will create it with sort of default values. So you might want to change the configuration of it. So you might want to change the proportional function to an integrator function. And that's easy to do. You just create an integration function, then replace the proportional function. And if we draw that out, that has now got the integrator function rather than the proportional function. And if we can print or get the output of the node that runs all the functions within that node, within that control unit, and that's the output of it in this case. And a particular node or control unit you can run a number of times as well. So that prints out each of the 4 functions within the control unit and prints it 10 times. But obviously you'd probably want to do this in the context of a hierarchy rather than just a single node or a single function. So you can create a PCT hierarchy. So in this case, I'm just creating a 2 by 2 hierarchy. And if I print the summary of that, that will show you 4 of the control units in a 2 by 2 array. And if we can print that out, and that's what it would look like graphically. It's created some automatic connections within it, some default connections. And you could create as many levels and sort of columns within a hierarchy as you wanted. So here's one I created earlier, and I saved it in a file. So I'm going to load this in, and this is which will run the inverted pendulum. And this is actually it's the cart pole environment from the Open AI gym. So here we have the 4 levels within the inverted pendulum. So at the top, there's the control system for the pole angle, then the pole velocity, cart position, and cart velocity. And this node down the bottom here, this is the environment itself. So this is the OpenAI Gym environment from which you are taking the perceptions of the state of the system, and then the output that goes into is the action that you're going to take. Within the OpenAI Gym, the actions it's either 1 or -1, so it's not sort of continuous. Okay, so we can run this. I hope this will come up with the. Yeah, can everybody see the inverted pendulum? Good. Okay, so that was just running the inverted pendulum with this PCT Python library. And you can see it was keeping the cart pole or the inverted pendulum balanced. Now that was just keeping the inverted pendulum in the same place. Now suppose you wanted to get the system to actually move around. So what we could do is add another node to the top of what we've just created. So which would do the control of the pole position rather than just balancing. So we can create another node, and here I've just done it in the textual format, so you can give a textual configuration to a particular node with the 4 standard PCT functions within them. So I create that node, then I can add it to the existing hierarchy which I already had. I'm just going to change a couple of things, so link this new node into what we already have. And then we can draw that out again. So this has now added the pole position control system to the top. So now it's got 5 levels, similar as to before. And then we can run that. I'll change that to 3000 so it runs for a while. So if we can see, okay. So it starts off by balancing, and the node which I've just added is actually the reference for it is a step function. So it's changing from the highest level reference of the pole position of 2 to -2. So the inverted pendulum will move back and forward. So hopefully for programmers anyway, this will be seen as a fairly easy way of creating control hierarchies quite simply. And the idea of this library, this is the initial version of it. So I'm hoping it's a possible common platform which people could use and share the systems that are doing and also contribute to it as well. Right, I think have we still got a bit of time left, I think? I'm just going to run through, I'm going to mention a few other libraries which might be of use. These are other Python libraries. There's one called Scipy, which gives you lots of statistical functionality. There's loads of things in this library. I haven't used any of them myself, actually. But there's probably lots of useful things with multivariate distributions, statistical functions, frequencies, correlations, all sorts of things. There's another library called Seaborn, and this is for doing statistical data visualization. Another library, which is part of the Plotlies actually, is called Dash. And this enables you to publish the Python programs as web applications. so you can put them online for other people to access and to use. And I'll just show a couple of examples of it in use. Okay, what's happened there? Let me just. Anyway, it allows you to create sort of drop-down boxes, buttons. Let's try, see if that gives you anything. Okay. Okay, so that's come up with a sort of dynamic plot. I'm not quite sure what this application does, but I'm just demonstrating that this gives you an environment for doing sort of dynamic and interactive demos online on the web. Another example here is one for viewing a brain in 3 dimensions, and you can. So this is an actual web page, and you can go on here and interact with it and dynamically move it around.
Okay.
And on the Dash website, there's a gallery of lots of different applications which people have created, which give you sort of examples of the sort of thing you can do. So the last library I was going to mention was Tensorflow, which is Google's machine learning platform for doing sort of deep learning. And this is an extremely powerful library which you can access, and you could merge it with PCT if you wanted, and I'll show you an example of that in a minute. So this is a sort of high performance distributed environment, and the idea behind it is to do what they call graph computations. So a system can be broken down into lots of different pieces in a graph-like way, where sort of inputs from nodes come from other nodes and outputs go to other nodes. So this is really quite well suited for PCT stuff. So they don't really have in here the concept of feedback, because it's sort of neural networks, which is all sort of more feed forward, but I've managed to sort of hack it a bit to make it work with PCT. It's also got a very good visualization system with it as well, so you can see all the weights changing as the system runs, and it's called TensorBoard, which goes with the platform of TensorFlow. So here's just an example of where I incorporated TensorFlow into the PCT system, and this is to do the reorganization of the inverted pendulum. So to reorganize the gains that the system has to improve the overall control, or reduce the global error within the system. I won't go into it too much, but this is within the Google Collaboratory environment, and this particular page is online. You can go and have a look at it. So this shows the error, the global error in improving over training. It's quite volatile, but the error goes down as the system reorganizes. Okay, and at the end there, it does go off the scale, and I'll show you why that is in a moment. So this is the graphical display of the TensorFlow, the deep learning platform, and this is the inverted pendulum implemented within TensorFlow, so within a deep learning system, which looks very similar to the architecture which I was just showing. And okay, so here this shows so this is a 3-dimensional plot of the error landscape of the inverted pendulum for 2 of the gain parameters. It's a little bit rough, but as you can see, it does sort of reduce down, and then at this point the parameters get unstable and the error sort of increases off the cliff edge, which is what we saw in the graph up the top there. Okay, so that's this page, and I put links to all this stuff on the slide so you can have those slides, and you can see all these pages. And the end here, it shows a video of the optimized inverted pendulum system. And here, the sort of global error of the running system is much better than it was previously. So it's gone down from 1.2 to around 0.25. Okay, let's go back to my first. Okay, so that's about it. So on the last slide, there's some more links. There's links to the sort of the PCT Python stuff, the documentation, some useful modules which are available for the Python libraries, which can be incorporated into the PCT system as well. Okay, that's it. Thank you very much.
Okay, great. Thank you. All right, so we're way over time limit, but let's go through some questions.
Hey, have you compared it with RL? This is from Tasif. Any comments on that comparison?
There's a lot of stuff, particularly for the inverted pendulum, and the reinforcement learning approach to it is very sort of long-winded. They have to build a quite complex neural network so they run the system a number of times and associate through the neural network the state of the system with actions that it takes at particular times. And with the reinforcement learning approach, you might have like 1,000 or 2,000 trainable parameters. Whereas with the system we saw just now, there's only 4 in the PCT system. So they're doing different things. But yeah, I was thinking of actually implementing the reinforcement learning approach myself to see, so I could really compare them properly. But you know, at the first glance, the reinforcement learning seems to be overcomplicated.
Okay, a question from Gary, which may not apply to programming specifically, but more how well, it's a design issue, I guess. How is gravity and the effects of acceleration, how are these variables handled in the inverted pendulum?
We don't need to worry about them. They're in part of the environment. So the environment is provided by, in this case, the OpenAI. So we're, within PCT, we're interested in modeling the organism itself. Obviously, it's always in the context of an environment.
That's an excellent point, actually, about the utility of this programming environment, because a lot of the code that people have been having to write has been to simulate the environment. And if you're given it with these tools, that's a real plus. Exactly.
I don't want to simulate the environment. There's a lot of work involved in it. I mean, ideally, I want to do them in the real world, so I don't have to simulate anything. We don't have to worry about gravity or anything. The PCT system adapts to the environment.
Yeah, that's terrific. Okay, from Eva, will you be sharing all these links for later access?
Yes, they're all on these slides here, and I can share the slides.
Okay. Nice. Here's a question to see. Philosophically speaking, I'm not sure what this means. NN go odds with PCT philosophy. I'm thinking to develop a PCT learner. Do you think it will have merit?
Sorry, I didn't quite understand.
NN, to see if maybe you can clarify. NN is at odds with PCT philosophy. I'm not sure.
I mean, in neural networks, as you mentioned already, it's a feed-forward learning process, whereas PCT goes in a feedback sort of a loop. But I think, which I didn't mention in the question, is when neural network initiates, it does a sort of a feedback thing, but instead of going back to the previous answer, it goes on refining the stuff, in an incremental way. So,
yeah, with neural networks, I see it being an iterative computation where the parameters are being refined on each iteration, but there's no feedback on the system in the sense that in PCT, where at each iteration the output of what we're doing is actually changing the
input.
That's the sort of the difference. So in this case, where the feedback is changing the input each time, whereas with neural networks you just feed in a bunch of images and you get an output, and then you use the error there to refine the parameters. But there's no actual feedback in the same sense that we're using here. So it's in fact that sort of immediate feedback on the environment, which is the difference here, I think.
Okay, two questions, one from Rick and one from Warren, and closely related. And the self-development of the system that you demonstrated there, is that like reorganization in PCT? And Warren says that kind of makes sense. Generating a PCT hierarchy through reorganization suggests connecting with Ben Hawker. So
that was in response to Tal's if he's thinking of a PCT learner, but I think it converges with what Rupert's doing.
Okay.
All right, are we satisfied?
Well,
no, I just wanted. Sorry.
Yeah, I was just going to say I'm going to be something I'm working on next is genetic algorithms to create the architectures of the PCT systems, to use that approach, because at the moment, you know, we're creating these hierarchies manually. So I was interested in looking at genetic algorithms to where they basically test out lots of different environments at the same time and see what they come up with. I think that might be a useful approach.
Okay, I actually, you missed one of my questions, which was simply, I think you answered it, but can it take input from a device like a mouse or something, so you can do interactive experimentation?
Yes.
Yes. If you're talking about yes.
I mean, are there timing issues or stuff like that? I can talk to you offline. That looks great. Okay, so we have to move on. Steve Battle is next. We're behind schedule, but there are many ways to. Oh yes, thank you, Rupert. That was great.
Yeah,
you're welcome.
Very exciting.